Hello, welcome back. Week 3 recording starting now. Um, we have a question. The question is, in these stud walls, are the mid-height noggins always at mid-height? And I guess to a great extent, the question is, what's the purpose of them? Um, so essentially, these studs, right, which are the vertical members in a stud wall, they're to frame like a wall. And you can put like plasterboard, or you put insulation in between it, in those like empty squares, and then you'd put like plasterboard or whatever walls are made out of on either side. So they're there to like structurally give the plasterboard um, strength, so that if someone like rams into it, for example, the whole wall's not going to fall and break, right? Um, so if you consider this stud wall as a part of like a bigger structural system, you'll see that these stud walls are designed to take tension and compression. So tension, in the case of uplift, when this top, I guess you'd call it a plate, this top plate gets pulled up due to like wind and suction, it would cause these members to elongate and be pulled in tension. That's case one, but if there's like a floor above it, which it says here there is, there'll be gravity loads. Well, there's self-weight as well, but like, since there is a floor here, there'd be fairly significant compressive loads on it. And we know that in compression, I've got sorry, you guys on Discord won't be able to see like my demonstration, but I'm showing the camera. Yeah, like basically when you compress like a 2x4, for example, timber member, it's going to buckle in the minor axis. So what we're looking at right now is like the thinner dimension of the stud wall, and then the deeper dimension is the one that goes into the page. And so it's more likely to buckle. Well, like if if it was completely unrestrained, it would just buckle in the minor axis basically and make like a C shape. But what these mid-height noggins do is it reduces the effective length. And if you put it at mid-height, what happens is you cut the effective length in half, right? So it becomes essentially like, instead of like 2.7, let's say it becomes like 1.35 of its effective length, right, in the minor axis. So it assists the minor axis so that it can't buckle. Instead of making like a C shape, it would be like an S shape that would have to buckle if we're looking at it. If I could draw it on top of this image easily, I would. But yeah, it would make like an S shape. You know, so that's like a lot harder than making the C shape. So yeah, it doesn't have to be a mid height. It could be like, if you have a really really long member, you might want to do it at like thirds or like, I don't know, quarters or whatever. But here they just do it at mid height because it's appropriate. You'll also see that it's a bit staggered. So, this stud, oh sorry, this noggin is like at this height, and then the next one is like a bit stepped down, and then the next one's step back up. And that's for like a buildability purpose, because if you think about how they're going to install these, they'll use like a nail gun or like maybe like a screwdriver and drive the connection going into the end grain of the wood. And think about it, you physically cannot get connections on either side of the noggins if you had it all at the same height, right? Like, try putting like a screwdriver like there. He's not going to be able to get anything in there. We'll talk about connections more in week 4, but yeah, hopefully that makes sense. If you guys have any questions, just drop it in the chat. Oh, okay. I see a question. So it always affects the S4 slenderness calculations. It'll always only affect the S4 slenderness calculations. So the S4 slenderness calculations are the minor axis slenderness, and yeah, so it would reduce the slenderness because when you have a shorter length to like width ratio, your member's like less slender and therefore it's less susceptible to buckling. And yeah, like I guess the purpose of it is to restrain the minor axis rather than the major axis, because the major axis doesn't need as much help as the minor axis, if that makes sense. It can resist buckling for like a longer length than the minor axis can. Okay, cool. Let's get into the stream. How do I do that? Let me just check my recording's working. Yeah, it looks like it is. Okay, great. Cool. So, we're gonna talk about. Let me just check I'm on the right thing. We're gonna talk about a couple things today, but mainly beam design. So, last week we did like column design / compression members. Here we'll do beam design. You'll notice that the weeks are switched up. Yeah, because I've rearranged how the course is taught. So we've actually covered part of this already. What we can do. One second. Just to reiterate, we have the phi factor and the K1 factor, which I've simplified here. So these are just like basically like excerpts from those tables as a summary, which will be relevant for this week. Like in later weeks, when we talk about connections, you have to use a different phi factor for. Sorry, not phi factor. You have to use a different. Oh no, I think you do have to use a different phi factor, and you have to use a different K1 factor for connections. So I do like another version of this table in like a later week's notes, right? But yeah, so phi factors taking into account like the building's purpose, and basically like the more like high risk your building is, or the more important it is, like if it fails, we kind of over design a bit more. Therefore we have like we assume that the capacity is much weaker than it actually is. And then with K1, that's like reducing depending on like the load case. So if you're dealing with just dead load, we're talking about like 50 plus years of loading, in which case like the timber gets really weak because of timber creeping. So just yeah, it will reduce the strength by like 43%. That's all recapping. So we talked about K4 factor as well last week, so I won't get too much into it. It's basically a partial seasoning factor if you have something that's not fully seasoned or fully. Sorry, if we have something seasoned and you put it in like a wet environment, it's going to change the properties a little bit. Or if you get something that's unseasoned, it's not fully dry yet, and you put it in a very dry environment for a long enough period of time, it's going to affect the strength. And then temperature factor is like if you're north of this basically line that's drawn here. So if you're in like Darwin or like Townsville, etc., you have to reduce your timber's capacity by 10% to account for that. Okay, strength sharing factor. Now this is unique to beams and like bending elements basically. So a beam isn't like bending isn't exclusive to a beam, right? But in the code they describe this part of the code as like the beam section, just because like the primary purpose of a beam is to bend. Like you can get a column that's taking bending, but that's not like the primary thing you're designing a column to do. So yeah, anyway, so if we have like beams, they can basically like you can have multiple timber members like grouped together, or you can have multiple like either individual timber members or groups of members running in parallel, right? And so we have terms for this. So ncom is like how many grouped elements you have, and then nmem is like how many members you have like working in parallel with each other and then like helping each other out basically. And so the K9 factor is actually like one of the only factors which isn't a reduction factor. I think it strictly increases your timber strength. Oh, actually, don't quote me on that. I'm pretty sure it only increases your strength or is 1. But yeah, anyway. So G31 and G32 are basically, they're called geometric shape factors, but they're just like an intermediate variable which you need to calculate to get your actual value that you're going to use in your calculations, called K9. Yeah. Okay. Is that right? Less than or equal to 1. 1 second. I'm a bit sus of my notes here. K9. K9 table 2.7. But not less than 1. But not less than 1, which means but not less than 1. So it has to be greater than 1, right? Am I going crazy? I'm pretty sure it has to be greater than 1 if it says but not less than 1. I'm going to put this in chat and then someone sanity check me, please. Anyway, yeah. Okay. Moving on. I think it's like it's 1 or more. I think it's a like strength increasing factor. Because you have multiple members working together and like bolstering the strength of your system, basically. Okay, stability factor. So we actually talked about stability factor a little bit last week, but it's a different stability factor. So you know how you guys were doing calcs with S3 and S4, where S3 is like the major axis compression slenderness, and then S4 is the minor axis compression slenderness. So now we have S1 and S2, and basically this is the one for bending, right, / beams, and it just uses a different part of the code, but it's very similar in how it's laid out. Like from a physics, like fundamental point of view, it's different, and I'll explain why, because I've got an example. Okay, so this is a function of that. Yep, so there's a table 3.1, and it's the material constant table, so rho and then subscript B. So B is for beams, and before we had rho C for columns. So this is just a different table. Keep in mind, and this applied as well for rho C, this is for when you have an R value of 0.25, and R is your temporary loads. I'm getting some validation in the chat saying greater than or equal to 1. Yeah. Okay, so yeah, I think I was right the second time. Anyway, R is your kind of like, what's a good word for it? Ratio of temporary loads to total loads. And then it just assumes that this is 0.25, right? But if your load case is just wind, R is basically 1, because your wind load is your total load. That makes sense? And to get the values for that load case, you can look in the appendix E for that. And I've also included it for my compression notes, I believe. But yeah, like this is pretty specific, and I feel like in an exam they're not gonna like dock you marks for using the values out of this table. I think it's more like maybe an assignment if you want to be like really diligent. Then I would do that. Anyway, yeah, slenderness coefficient. We have bending about the major axis and bending about the minor axis. But the thing is, here's where it's different. S2 is always 0. So we're just focusing on S1, right? And that's because of the nature of flexural buckling, right? Which I'll explain in a second. Okay, and then similar idea to before, we have three different formulas depending on if you have compact, non-compact, or slender members, right? Okay, so here's how I explained this flexural buckling concept in steels when I taught that earlier this year. And how to explain it? I have like my little like wooden ruler thing, but the people on Discord won't be able to see it, so I'll just try and kind of explain it by drawing it first. So if you imagine, let's just say, because it applies very similarly for steel beams, right? Because they're also steel beams and timber beams, right? Let's just draw timber like that, right? They're similar in that they'll end up being like these slender, long members, and what else is there to say about that? Yeah, like, they're slender because, like, if you had a steel beam that was really chunky, for example, like this, it's less susceptible to flexural buckling, right? It's the fact that we're trying to essentially optimize our material to like get as much done as possible with as thin of a section as possible, is why we have to deal with flexural buckling. And for timber, it just happens to be that, I guess, I don't know. Timber's just a rectangular cross section for the most part, right? Like sawn timber. If you have like concrete, for example, you might have like concrete beams and a slab, for example. And then these beams are bending and whatever, but essentially the slab is acting as a restraint, and you'll see what I mean in a second. So you don't really get flexural buckling in concrete. So that was just highlighting the difference between the materials. Let's talk about it like this, right? So say you have a timber beam, that's this section, and here's looking at it side on, and here's like the supports, here's like side grain, or whatever, right? You put a load on it, okay, and what am I doing? Yeah, if you put a load on it like this, it's basically gonna deform. Let's do it in purple. It's gonna deform in this shape, right? And if we draw a section, we're looking at that basically, right? So that's the section, and what you'll find is that as you load the beam, the deformed shape, which I've drawn in purple here, it's gonna go down, right? But since it's slender, right? So in the minor axis, right, going left and right, it's like weaker than the major axis, so going up and down, right? What actually happens? Oh, fuck. I'm gonna draw it like this, yeah. Let's draw the strain profile, right? So if we have like this normal gravity load situation going on, we have compression happening at the top and tension happening at the bottom, right? So what happens is we know that in compression, a member wants to essentially buckle out in the minor axis, like when you have a difference in the minor and major axis directions. So the top actually wants to buckle out, like, you know, left and right, because that's the minor axis direction, right? But the bottom is actually being pulled in tension, right? And so what ends up happening is this happens, right? Let's draw it like that. So you have this going on, which is your vertical deflection, right? So that, whatever that distance is, and then you also at the top here have your horizontal, let's say like compression buckling, Actually, a better word for it. Lateral deflection. But at the bottom it's being pulled, so it wants to stay back in its original kind of position. Kind of like how when you pull a rope, it gets tighter and then like all the slack goes out, right? Um, but so as a result of this difference, right, what happens is you get this twist, right? And this twist is called torsion, right? So this phenomenon of flexural buckling, I'm using like kind of an unofficial term, like flexural buckling. People know what you're talking about, but the like actual scientific term is called lateral torsional buckling, right? You might have heard this before, but it's used like if you're looking at the lectures and stuff in steels, this is what they were talking about. So that's what like flexural buckling is, right? So yeah, like let me know in the chat if you have any questions, but hopefully that makes sense. So that happens when you are bending a member that has like a difference in the major and minor axis, basically. Cool. And is there anything else to say about that? Not really. Oh, sorry, I should say, I guess S1 is the one you're focusing on because we're talking about major axis like bending here, right? Minor axis bending, like this phenomenon. Wait, let me think about this. I'll think about that and then talk about it next week because I can't think of the exact string of logic why S2 is 0 right now without looking like at the formulas deeply. Okay, anyway, let's just focus on S1 for now, right? So I've drawn, so this is what's in the code, right? And then this is what I've kind of just drawn as a simplification, right? So if you have downwards load and you're restraining the compression flange, right? Which is the top flange. So imagine we had that scenario before, but you've put restraint here at the top, like that. It will stop the buckling from happening, like in the compression side. Sorry, I'm used to saying flange because in steels, that's your top flange, right? But like here, I should just say the compression side, right, of your member. But here, there's a different formula if you restrain the tension edge, right? So we have wind reversal happening, but we restrain the top. Now, this part of the code still applies if you restrain the bottom instead, and it was downwards force. I should draw it on the other one. Like, let's just say instead of those restraints, you restrain the bottom ones, then you basically are looking at that scenario. You know what I mean? Hopefully you know what I mean. Okay. Okay, and then if you have continuous restraint, so discrete restraint is like kind of like how last week in compression we had the stud wall and like noggin system, like I was talking about before. That's like a discrete restraint, right? Like the noggins are a discrete restraint. But if you have a continuous restraint, such as nails, and like you have the floorboard holding your whole thing together, use a different formula basically. Well, in fact, S1 is 0 as long as this thing applies, as long as this formula applies. That's what it's saying. So if S1 0, or if S2 0, that means they're not slender, I think, in that direction, which means they're compact, which means you won't be dealing with flexural buckling. Okay. I've thought about it. So what I was saying earlier is you don't consider, so if you have bending happening in your minor axis, right? So imagine I have like a ruler for you guys online. Basically a ruler. So it's like really weak in that direction. And you're bending it in the minor axis direction. you don't have to consider lateral torsional buckling because your minor axis bending is just going to fail. Like, sorry, your minor axis is going to fail before your major axis, right? And so you're not going to have the lateral torsional buckling effect happening, because for lateral torsional buckling to happen, the minor axis has to fail before the major axis. No, you're bending in the major axis, and then the minor axis is gonna like basically be your point of failure. That's what I'm trying to say. But if you're bending in the minor axis, your minor axis is already your point of failure, so you don't have to consider lateral torsional buckling. Okay, fuck. I hope that made sense. Give a shout if it didn't make sense. But yeah. And so similarly, if you have continuous restraint, you don't have to consider lateral torsional buckling because the lateral torsional buckling won't happen, right? That's continuous restraint along the compression edge. And in the tension edge, it's a different formula. And torsional restraints, so this is like fly bracing. So imagine in that little diagram I drew before, instead of having like a top or bottom restraint, we specifically have these kind of diagonals that aren't really restraining it from going left and right or like laterally, but it's restraining the twist from happening, right? That's a torsional restraint. And then you got a completely different formula for that as well. So those are all the different scenarios you have to consider. Cool. Okay, so getting to the design of beams. I guess Nathaniel, you haven't done steels yet, right? But yeah, hopefully most of you guys have done steels. I'm gonna use some steel analogies here. Basically in steels, as a recap, you have NS. No, I shouldn't say NS. You should have MS, which is your sectional capacity, and you have MB, which is your member capacity in bending. Bending section capacity. And this is your bending member capacity, right? So in this course, like, don't use these terms because these are for the steels code, right? But I'm just going to use the analogy just so you guys can understand what's going on. Basically, here's your section capacity equivalent, right? FB is your strength in bending, right? Which comes from a table, depending on your type of wood. And Z is your elastic section modulus, right? And since we're dealing with rectangular sections, for the most part in this course, it's just going to be this formula, right? So Z, you can think of, okay, here's how I explained it when I was like teaching steels, right? Basically, a force is equal to a stress times area, right? So, you know, a stress is equal to a force times force divided by area, and so when you rearrange it, you can get a force is equal to a stress times area, right? Similarly, your moment is equal to your stress times your elastic section modulus, right? If it's an elastic material, and will break, like if we consider it to break suddenly. So in like for timber bending design, right? If that's tension, right? We're considering just the elastic part of the material curve. If you're doing that, like relatively conservatively, no, I shouldn't say relatively conservatively. That's just like how the code's set up, right? We're considering the bending failure mode to be brittle, right? So we can use the elastic section modulus because this is a brittle failure, right? Yeah. Anyway, that's how that can be explained, right? This portion here is just your section capacity. Okay. Now in steels, if you do like phi ms, right? You take into account like your capacity reduction factor, so that in steels, right? This is steels. I'm just gonna write steels so that no one writes this down because this is a different course, right? In steels, that'd be 0.9, right? And so what you would do in this course is you apply all of these factors, right? I've deliberately not highlighted K12 here, right? And that would essentially, like, your phi multiplied by all your K factors from K1 to K9 would be the equivalent of doing just this simple phi factor in steels. It's just because we have more modification factors than timber. Like, we've learned how timber just behaves more complicatedly, I guess. Yeah, due to like temperature, moisture, etc. So yeah, that's that. And then lastly we have K12 factor, right? K12 factor was our stability factor, right? Which is a function of your slenderness, right? Which is, when you multiply that whole thing together, sorry, when you multiply these two together, you basically get MB, okay? So the formula for MB was like alpha C MS, right, in steels. To some degree, your K12 factor is your alpha C equivalent, right? So essentially, yeah, that's kind of how this code is set up. This is written by different people, even though it's like all the Australian standards, and the researchers decided to set it up this way rather than the same way as steels, and so it's, yeah. Anyway, it just looks different, right? So that's that. Yeah, cool. Looking in the chat if anyone has questions. Nope. Okay, cool. Okay, so I'm kind of going slow. I haven't talked about too much yet. So biaxial bending is like, let's just say, we have a beam like this, right? Just drawing it in 3D, and we have horizontal wind load, for example, and we also have some kind of load from above, G, Q, whatever. If we have this, we have biaxial bending, right? In the major direction here, whatever this bending moment is, that is going to cause like mx, right? So the bending moment in the major axis direction, and whatever the bending moment caused by wind is in the minor direction, that's m star y, right? And then we have our corresponding design calculations, like the capacity calculations for both directions. Yeah, so you would basically just switch around, for example, B and D, when you're calculating Z, because your width and your depth directions are like different, right, for minor axis. Okay, cool. So that's bending. Oh yeah, this is just like an additional check if you have biaxial bending, basically. The combination of the action being like the vertical direction and the horizontal direction. Like, this is just a ratio, right? It's like, there's this term called utilization. It's been a long day. Utilization, right? Utilization. So it's like, if your major axis, right, is working at like 40% utilization, so 40% of the load that it can handle, right, is being used, and your minor axis is like 50%, right? The addition of those two utilizations has to be less than 100%. That's what this formula is trying to say, right? Okay. Okay, timber in flexural shear. So how to explain shear? Shear is basically like, so if we have a beam, right? Shear is the perpendicular force that's trying to slice your member, right? In half. Yeah. And it's particularly bad if you have point loads, right? So if you had a big fat point load, say in the middle, then your shear force diagram would look like this, right? And it would do a big jump. But if we just have a UDL, the shear force diagram looks like that, right? And your highest shear is at the edges, right? Or at the supports, but the support itself will provide a bit of strength as well in reality, so it's like a little bit away from the support is where you'd expect it to fail. You also expect it not to directly slice something in half like that. I guess because of like the deformed shape, it'll kind of fall out like that, right? More so. So yeah. Similar setup. We have our standard factors, which we've been talking about even for like tension and compression, right? We've got a temperature factor, partial seasoning factor, capacity factor, and load duration. Hello. Oh, hello. Sorry, I'm back. My headset doesn't like to last more than 1 hour. Okay, anyway. Where were we? Oh yeah, so back to this. So we have a shear strength, right? Which you can find again from tables. Yeah, tables depending on the type of tree, etc. Shear plane area is this for rectangles. So basically, if you recall, there's like a formula which describes shear, right? Like at any given point, shear stress, you can like plot it. And one sec, I'm suspicious of what I've written as well. Shear strength. Oh, okay, no, that's right. Okay, never mind. Sorry. So yes, that's that. I think the idea is that if you look at the okay, let me try to re-explain this again. Right. So if you look at the shear stress, right, the most stress in a rectangular shape happens towards the middle, right? The top and the bottom aren't taking very much shear. It's almost like the opposite of what happens for bending stress, right? Because in bending stress, the top and the bottom, I guess, edges or those fibers are experiencing the most like bending stress, right? But shear stress wise, it's actually the middle, right? So I think what this formula is trying to tell us is if you have a rectangular shape, the middle 2/3, right? 2/3 BD, that's our conservative estimate for the shear area, right? I think that's what it's trying to say. Okay, cool. I might expand on this when I, because this is like a pretty mediocre explanation. I'll get back to you next week on that. Okay. And then yep, that's actually the rest is fairly straightforward. Next is bearing. So bearing is basically where you have two different solid objects, and they're in contact with each other, and they're compressing against each other, right? So this happens a lot at supports, right? Where you have like a column supporting a beam. The reaction is going to cause a compressive bearing onto the beam, right? So it's basically like crushing, not crushing. Yeah, this beam can fail in bearing basically, right? Based on that bearing area between the two solid objects. And we have three different formulas here. Don't get overwhelmed. This is basically based on direction. So P here stands for perpendicular to the grain. L stands for parallel to the grain. And theta stands for at a certain angle. So here I've got like a diagram which explains it from the code. It's actually quite a nice diagram. But the usual case I want to say is your perpendicular bearing, because what will often happen is you have like the grains for a beam, like longitudinally running along the beam, and then the grains for a column running up and down longitudinally for the column, and so you're going to run into this perpendicular grain scenario more commonly. So this will be the formula you're following most of the time. Keep in mind that also have different values for strength in the tables, like for the different tree types and things like that. Yeah. AP. Yeah, again, it's just like the bearing area. So whatever surface contact area is happening, that's what you're considering. And K7, I'm gonna explain K7. And this is a special factor for perpendicular bearing, and I believe it's a strength increasing factor. Yeah, so long as your beam has like enough overhang, right? So it's not too close to the edge. Either overhang, or if it's like this, right? Where your beam's not even close to an edge, right? So if that's a column and you have a beam and it just keeps running and it's supported even further, like left and further right, you can use this formula, right? So it just can't be too close to the edge, right? So if your beam ends like here, for example, you can't use this bearing strength increasing factor. But in this scenario you can, and in this scenario where it's greater than 75 mil of overhang, then you can. And yeah, so it's based on the length of your bearing member. You're allowed to increase your strength, essentially, right? And this is kind of just a way of bolstering, essentially, your bearing area. You can think of it like that. So yeah, if you have like a short bearing length like this, but you have enough overhang, you can consider more bearing length, essentially. Maybe not that much. You can like multiply it by a certain amount, essentially. Hopefully that makes sense. Okay, cool. Serviceability. So serviceability is quite different to what we just talked about. So we talked about bending, we talked about shear, and we talked about bearing. And these are all part of the same section of the code. It's basically like beam design for strength, right? For timber members. Here we're doing serviceability design. Now this is still essentially like the loading scenario is the same, right? So let's just say we have a simply supported beam, and there's a uniformly distributed load on it. And essentially your beam is going to sag, right? And we're focusing on the sag rather than whether it's going to break or not now, right? So that's what serviceability is. We have different load scenarios. So before we were considering, 1.2. I shouldn't say that. Let's do the uniformly distributed load. So that load was like this, for example. It's one of the load combinations. So those are the strength load combinations. There's that. There's this one. There's the wind ones, etc. Right? When we're considering this part of the code, just completely disregard that, because we're working with an entirely different kind of philosophy when we're doing serviceability design. So we have ultimate/strength design. These are called limit states, right? Limit state design. We have the ultimate / strength limit state, and we have the serviceability limit state. Broadly speaking, these are the main things you're checking. And then there's like subcategories and things like that. So in the serviceability limit state, instead of using, I'm just going to bring this over to the other page for more space. Instead of using these load combinations, instead, right, you would be using, so this is factored for serviceability, that's what I'm writing here. You would be doing like G plus stuff like this. Let's keep the notation consistent. Phi SQ, or like WG plus phi LQ. And these are your short and long term loading scenarios, right? So your short term is 0.7 and long term is 0.4 for most scenarios, unless you have like storage buildings and things like that. And so just generally speaking, these are everyday loads, so serviceability loads. You're designing your beam to resist everyday loads essentially, right? Where people like walk on it, you don't want there to be bounce when you're walking on it. You don't want to look up and see that your concrete slab in the building that you're in is sagging, things like that. Yeah, so instead of an exaggeration factor for the worst case scenario, we're essentially dealing with toned down versions of your live load, and it's just a factor of 1 for your dead loads, right? So this is a description of AS1170. And how it applies to timber is, if we're focusing on the deflection, right? We have elastic deflection, which is pretty much just what I described. And then in the timber code, we have to multiply it by this J2 factor. And J2 is a creep deformation factor. So I think either in the first week or last week, I alluded to the fact that timber creeping affects both its strength, right? Because before we were talking about the K1 factor and how you can lose up to like 43% of timber strength over a long time. Here we have creeping affecting serviceability, right? You'll see that like over a couple years, I can't remember the exact numbers off the top of my head, you'll get like double deflection or like triple deflection depending on like live and dead loads and things like that, right? Okay, so that's the left hand side. Right hand side, we had to make sure that whatever our deflection is has to be less than some sort of limit, right? This is usually provided in the question, and it's a function of your span, or there's guidelines for it in these two standards that I've mentioned, right? So you're like in industry, you're designing, you would jump to the standards and look at the guidelines, because you're not given like a perfect question where the lecturer tells you what to design for. Anyway, an example would be like span on 250. So if you have like a 10 meter long beam, right? Firstly, you convert that to millimeters, so it'd be 10,000 millimeters, right? And then you get that span, and you divide it by 250, which I can't do off the top of my head, and you get 40, right? So the limit of how far this can sag down in the middle is 40 millimeters, for example, right? So that's how that number would work. Oops. J2 factor is applied differently to dead and live loads. So essentially the codes doesn't really do a great job of telling you how this works. So firstly, there's two kind of columns to look at, right? There's the one for bending, compression, and shear members, and then there's a J3 factor for tension members, which I'm pretty sure you won't have to do the serviceability of tension members in this course. But yeah, so we'll mostly be focusing on the bending deformations. So yeah, so when you have a load acting for less than 1 day, you won't have a creep factor happening, right? But depending on the moisture content of your timber, if you have that load happen for more than a year, it's gonna be set to a certain number. And if it's any kind of value in between, you should interpolate as needed. And there's like a little graph here which you can kind of it's fucking stupid. You can kind of like, it's like a logarithmic kind of thing. I don't know. Yeah, you kind of just interpolate and try to read off the graph as best you can. Any questions? I think no questions so far, so we're gonna continue. So elastic deformation, right? I think we talked about this maybe very, very briefly at the end of the first week's video. Essentially, if you have a bunch of timber joists, right, for example, running in parallel to each other, the chance of all of those timber members you selected having the worst stiffness, worst elastic modulus imaginable is really low. So in the case where you have a lot of parallel members running, parallel floor joists supporting each other, right, or like assisting each other in carrying the loads, you can use E-mean, right? However, if you have a single timber member that's doing a lot of work by itself, you should use the worst case elastic modulus, right? And the worst case elastic modulus is different depending on what type of timber product you're using, right? So here I've highlighted it. Blue, there's F grades, green is MGP, yellow is both plywood and glue lam, has that number. LVL, a different number, and in red, LVL is orange, in red is A grade, which is like your mountain ash and stuff like that. Yep. Okay, cool. So here I've got your typical loading scenarios. So these are, I think they're derived from like first principles solid mechanics and things like that. It's kind of a pain in the ass to get these, but they're easily found online if you like Google for what's the deflection formula for like a simply supported beam with a uniformly distributed load acting on it. That's like the first scenario I just described. Or what's the deflection formula for a some sort of beam with fixed ends. No, I shouldn't say simply supported. A single span fixed supports beam with uniformly distributed loads acting on it. That's the formula there, etc. Right? Here you got the continuous one for two span continuous. Here you got simply supported point loaded down the middle. There'll be different ones for different loading scenarios. I think these ones will be the most common that you'll run into. But if you run into something weird, I would just Google it, or you can use ChatGPT or DeepSeek or something. Okay, so here's an example of how you would plug the numbers in. So you say you have a dead load of 3 kilonewtons per meter, and so you have a live load of 11 kilonewtons per meter, right? We have the formula from above, right? That is this one. Oops. So that's just the blanket formula for elastic deflection for simply supported beam with uniformly distributed loads, which is what we have here. So that's that there. What's different is how we apply. So there's kind of two things going on here. One, you'll notice that we don't have W in the formula, so that's W, and we've moved it out the front, right? So this is both the W component and the J2 component multiplied together. Okay, so loads is W, yeah, and for live loads, make sure you have the appropriate 5 factor as well. So remember that's 0.7. and that one for long term is 0.4. You basically put in your J2 value. And so basically dead loads, this is assuming you have greater than or equal to 1 year load. So the purpose of a dead load is supposed to be there for like a very long time, like 50 plus years, right? And so therefore it falls into the category of being greater than or equal to 1 year. And this one falls into the category of being, I guess, less than or equal to 1 year, right? Because again, it's short term, right? It's short term. But in the long term, right? So this one stays the same. This is greater than 1 year. Oh, sorry, I should say this is 1 day. I think it was. And then this one was. If you have a long-term live load, we're assuming this is greater than or equal to 1 year. Okay, that's what it's trying to say. So like if this was like for a dead load, if this in reality was like 50 years, a long-term live load might be like, for example, like 2 years or like 3 years. Yeah, that makes sense from like a logical point of view. Whereas a short-term live load, yeah, it could be like less than a day. It could be like some dude standing there and then he decides to move in like 5 minutes. Whereas the long-term live load, just give an example, would be like, say you have like a grand piano that's on wheels and it might move from place to place, right? That would be like a long-term live load. Okay, vibration. I'll cover this if it actually comes up more in the questions, but I won't get too into it because in previous years it wasn't really accessible. The idea is if you put a point load, right, of 1 kilonewton multiplied by G for 1, right, in the middle of your structural member, right, you have to check that this deflection doesn't exceed 1 to 2 millimeters, right? This is just like, it's like a variation of your normal deflection checks on your floor, right? It's just like a random point load of some dude stepping on there, I guess. It has to be less than a flat limit of some sort. And yeah, I'll kind of just leave this for you guys to read up on, but I'm not going to cover it in depth because it might not be very accessible. Yeah, similarly to last week, sorry, I'm not going to really go into the questions here. These videos, I just want them to be like as concise as possible, but yeah, I've provided the question and my solutions for this, and just have a read, because this week with the bending design, the serviceability design, it's super important. Designing beams is like the first thing that you got to learn how to do, and yes, like for timber, that's like especially true. No, that doesn't make any sense. What am I saying? They teach you how to design beams for every structural design course, like for steels and for concrete, and that's like one of the main takeaways, and it's no different for timber. That's what I was trying to say. And so yeah, it's very important to learn how to design a beam, timber beam. So yeah, I've got a bunch of just random examples and stuff. These are all in my Google Drive and notes, so if you want to scroll through these more thoroughly, we can do that. Rather, you can do that. Because yeah, there's no point in me going through it because it's just going to make the video like much longer, and it's a lot easier just to read through the solutions yourself. So I'm going to touch on one more thing, which is what I've added to my week 3 notes, because last week when I was doing the recording I said that these notes were incomplete. What I've added is this page, right? It's very similar to how I was talking about biaxial bending today, right? So when you had like maybe wind causing bending in the minor axis of your beam and maybe like vertical loads causing major axis bending, right? Similar here, but it's when you combine tension and bending, and when you combine compression and bending, you have to do like additional checks, right? So there's 2 checks each that you have to check. So essentially we're quote unquote dividing out K12 of this first one, right? So remember how I was comparing timber to steels, right? So for MD, right, I'm going to test my memory. The formula looked like this. Formula looked like that. And in steels, we had MB is equal to alpha C MS, right? Sure, let's just add the 5 factor as well, right? So if we just focus on this, right? MD is essentially MS times yeah, anyway, point is, what I'm trying to say is like we don't consider the K12 or like the equivalent of the alpha C component in this first utilization, right? So we divide out K12 essentially of MD, and that gives us the bending section utilization, right? So how much of the member is used if we just disregard any reduction in strength due to flexural buckling, right? That's what that's trying to say. And you add that to your tension utilization, so how much it's being pulled versus how much it can take. And again, yeah, it would be, just to give the same numbers, it'd be like 40% utilization, for example, 50% utilization. This has to be less than 100% utilization. If it is, then it's okay. So that's that first one. This next one is the member utilization. So we're considering the whole thing here, right? So including if it experiences flexural buckling. And then basically, so I'm going to draw this. So that's our stress curve. Here's our timber beam, and here's our timber section, right? And we were looking like that. And you know how we had like the lateral torsional buckling effects happening like that? And essentially it's because we had compression on the top and tension at the bottom, right? What happens if we pull the entire thing everywhere, right, in tension, right? So this basically, if we added that effect on, right, we can add these stresses together, and the net stress would be more of the whole thing in tension than compression, right? And remember, buckling happens on the compression side, essentially, right? And so here we're subtracting because tension is actually beneficial versus flexural buckling, right? And so we have to just check that the flexural utilization and tension combined is not going to fail, right? That's what that one's saying. Okay, and then combined compression and bending check. Okay, these ones are pretty similar, so I'll talk about them at the same time. Will I? Oops. Okay, so same thing as before, but imagine instead of tension, we also had just like a compressive force happening on it, well, you would basically have an adverse effect, right? Because more compression's happening and therefore it's more susceptible to buckling, right? So you have your regular flexural bending compression, and then you're adding on like a flat amount of axial compression as well. And so that combined effect is really bad, right? And the idea is that remember, like S4 is your slenderness factor in the minor axis, right? So that top one is checking for that minor axis, the minor axis utilization and the bending utilization at the same time. I'm going to comment on this note in a second. And similar idea, major axis, you're checking for major axis, so like the S3 slenderness capacity, and your flexural buckling together, right? But the difference is, this one's essentially usually worse, and so here, to be honest, I haven't done a deep dive into the code commentary. Usually there's like supplementary commentary on like the codes as they're written on why certain decisions like this are made. The fact that it's squared, right? But someone decided to do it like this, right? When you square a term that's less than 0, right? Because we're assuming that this is... Because if it's like already 110%, right? And you square it, it's going to make it worse. But the idea is that if it's failing... if bending is failing and like over 100% anyway, your beam's fucked, regardless if you have compression or not. So this will be a number that's less than 100%. Say it's like, I don't know, let's just say like 50%, right? You have 50% and you square it, it becomes 25%, right? So it make it better. You add that onto your YY compression minor axis utilization, and hopefully that number's less than 100, and you check the same, but you don't square it for the major axis one, and then yeah, that's the checks. Okay. Oh, sorry, I got a question 5 minutes ago. So we don't consider K12 at all for the first case in combined tension and bending. So that's a good question. So, like, for the first case, yes, because you're basically doing the section check. How do I say it? So for tension and bending, right? We're checking. We're doing 2 checks. The first one's basically the combination of tension and bending without flexural buckling involved. And then you're considering with flexural buckling involved. So like, you got to check for both, basically. That's what the 2 checks are saying. And if either one of them fails, your beam's failing. That's decoding what these formulas are trying to say, basically. Cool. If anyone else has questions, drop it. But otherwise, that will be the end of today. Thank you for tuning in, and we'll talk about connections next week.